G of t, then set G of t of ordered pairs of ordered pairs ordered pairs x comma t of x comma t of x is called graph of t, is called graph of t. Graph of t and written as g of t equal to means graph of t equal to x comma t of x tx such that x belongs to the x belongs to here clearly g of t is subspace of g of t is subspace of g of t is subspace of b cross b dash cross b dash. Next, most important thing before closes off before 8.4.1 theorem. 8.4.1 8.4.1 theorem. Statement that B and B dash two Banach spaces. B and B dash two Banach spaces. B and B dash two Banach spaces. Suppose T B to B dash be linear let D be a subspace of B. D be a subspace of B. And T D to B dash then T is a closed linear transformation. Closed linear transformation. Closed linear transformation from B into B dash. From B into B dash. B into B dash. If and only if its graph G of T is, the symbol is known as if and only if its graph G of T is closed subspace of B cross B dash Proof. Before proving closure graph, we need to prove this thing. Let P d2 b dash d2 b dash, where D is the subspace of B, where D is the subspace of B, where D is the subspace of B. T is a closed linear transformation. T is a closed linear transformation. T is a linear closed transformation. Linear transformation. Linear transformation. We need to show that G of T. We need to show that. We need to prove that G of T equal to x comma T of x such that x belongs to D. X belongs to D. In a closed subspace, T is a linear closed subspace. Closed subspace. Since T is a linear, G of T is subgraph. Here G of T is subgraph. Subgraph. So every point, limit point of G of T belongs to G of T. Every point, PT means point, every point G of T, every point, limit point of G of T, limit point of G of T belongs to G of T. G of T. So let x comma y be a limit point of G of T, which implies let x comma y be a limit point which implies sequence of point, which implies sequence of points. Sequence of point means xn comma t of xn, t of xn. In G of T, where xn belongs to D, xn belongs to D, such that the sequence xn comma txn tends to x comma y. That implies xn comma txn tends to x comma y that tends to 0. That implies norm of xn minus x tends to 0 and norm of txn minus y tends to 0 that implies xn minus x and txn tends to y. So since t is closer, we have since t is close, since t is close, since t is close, we have x belongs to t and x belongs to t and y equal to p of x. Y equal to p of x. Therefore, limit point x comma y. Therefore, limit point x comma y that equal to x comma dx that belongs to g of t. That implies g of t is closed here. G of t is closed. Conversely, g of t is closed with subspace. Conversely, g of t is closed. G of t is closed with subspace. G of t is closed with subspace. Clearly, t is linear. Clearly, t is linear. So that xn tends to here, xn tends to x, and where xn belongs to d. For all n, t of xn tends to y. So t is closed. T is closed. That means y equal to p of x. That means since xn comma t of xn tends to x comma y. What is x comma y? X comma y is the limit points. That means x comma y belongs to g of t. Wow. So g of t is closed. So g of t equal to g of t whole bar equal to whole bar. That implies x comma y belongs to g of t. X comma y belongs to g of t. So Hence, by definition of B of t, x belongs to D and y equal to t of x. Y equal to t of x. What equal to p is closed. This completes the proof. Hence proved. Hence proved. Most important theorem, 8.4.2. Closed graph theorem. 8.4.2. 8.4.2. 8.4.2. Closed graph theorem. Closed graph theorem. Closed graph theorem. Closed graph statement. Closed graph theorem statement. If B and B dash Banach spaces, if B and B dash BS means Banach spaces, and if T is a linear transformation, and if T is a linear transformation, if T is a linear transformation of B into B dash, B into B dash, B into B dash, then T is a continuous, then T is a CTS means continuous, T is a continuous, if and only if its graph is closed. This is the if and only if symbol. If and only if its graph is closed. So graph is closed. Graph is closed. Proof. First, we need to prove that T is a closed when given T is continuous. We need to prove that T is closed. T is closed. T is closed when T is continuous. T is CTS means continuous. So let it xn T xn xn T xn xn T xn. We sequence in graph. Sequence in graph. Sequence in graph. G of T. G of T. ST means such that xn, comma txn. Xn, comma txn. That's to x comma y. X comma y belongs to B into B cross B into B cross. That implies norm of xn comma txn, xn comma txn tends to x comma y tends to 0. Tends to 0. That implies norm of That implies norm of xn minus x. Norm of xn minus x plus norm of txn. Norm of txn minus y tends to 0 as n tends to infinity. N tends to infinity. So that implies xn minus x tends to 0. That implies norm xn minus x tends to 0 and norm of txn minus y tends to 0 as n tends to infinity. N tends to infinity. T is a continuous, follows that T is continuous, follows that xn tends to x. Xn tends to x. That implies T of xn tends to T of x. T of xn tends to T of x. So that means norm of txn minus y tends to 0 and norm of txn minus tx tends to 0 as n tends to infinity. So uniqueness of the limit, we have y equal to t of x, y equal to t of x. The graph of g is closed. Thus, the graph of g of t is closed. Graph of g of t is closed. Next, conversely, suppose that g of t is closed, t is continuous. Conversely, suppose that norm of txn conversely suppose that g of t is closed. G of t is closed. We show that t is continuous. We need to prove that. T is continuous. We use CTS, means continuous. Define B1 as the linear space of B. Define B1 as the linear space of B. As the linear space of B. With new norm. New norm is norm of x1. That equal to norm of x plus norm of t of x, tx. B1 is equipped, means embedded in normal linear space. Thus, B1 is equipped, means embedded. Equipped means fixed. Equipped. And new norm, new NLS means new normal linear space. So for first one, so norm of 1 is greater than or equal to 0. Since norm x greater than or equal to 0. Norm x equal to, and norm of t of x, norm of t of x greater than or equal to 0. That implies norm 1 plus norm of tx, norm of tx is greater than or equal to 0 for all x belongs to, for all x belongs to B. X belongs to B. Second. So norm of x1 equal to 0. Norm of x1 equal to 0. If and only if, this symbol is known as double implication. If and only if norm x plus norm of tx equal to 0. If and only if, and only if norm of x equal to 0 and norm of p of x equal to 0. If and only if x equal to 0. Third property. Norm of alpha x1. Here, norm of alpha x. That equal to norm of alpha x plus p of norm of p alpha x, alpha x. That equal to norm of alpha x plus norm of that equal to alpha x norm of alpha. So norm of alpha p of x, alpha p of x. This can be written as that equal to, the alpha is mod alpha, here mod alpha, into norm of x plus mod alpha norm of t of x, norm of t of x. Here alpha is both the things is common. We need to take mod alpha is common, whole common. We can write norm x plus norm of t of x, norm of t of x. Right. Next, fourth property. Fourth property, what is that? Norm of x plus y, norm of x plus y. That equal to norm of x plus y, norm of x plus y plus t of, so norm of t of x plus y, x plus y. That equal to norm of, that equal to norm of x plus y, norm of x plus y plus norm of t of x plus t of y, t of x plus t of y. Here t is a linear, t is linear, t is linear. That's why we are writing t of x plus y. We wrote t of x plus t of y. That means inequality can be written as less than or equal to, less than or equal to, less than or equal to norm of x plus norm of y, norm of x plus norm of y plus norm of p of x plus norm of p of y, norm of p of y. Here, join the like terms. That equal to, join the like terms means norm of x plus norm of t of x, plus norm of y plus norm of t of y. Norm of t of y. So these are all nothing but here this part under two parts. This becomes nothing but nothing but it is the norm of norm of x1 plus norm of y1 new norms. Here norm is a on norm is a norm, that means that implies here norm 1 is a norm on B and space 1 on B and the space B1 space and space B1 equipped with the new norm, equipped or embedded or fixed, equipped with the new norm, normal linear space. NLS means normal linear space. Here P1 comma 1 is a normal linear space. Here NLS means normal linear space. So B1 is complete with respect to the new norm. B1 is complete. Here B1 is complete with the new norm. Complete with the new norm. Let xn be a Cauchy sequence in B dash. Let sequence xn is a Cauchy sequence. Cauchy sequence in B1. But the definition of norm follows that x and txn are Cauchy. It follows that means that implies xn and t of xn be two Cauchy sequences. B and B dash respectively. B and B dash respectively. Here B and B dash are complete. B and B dash complete. Are complete. It follows that there exists x belongs to. It follows that there exists x belongs to B. And y belongs to B dash. Y belongs to B dash such that xn tends to x. And t of xn tends to y. So by closeness of the graph, it follows that y equal to t of x. Y equal to 2. Now norm xn plus x. That equal to norm xn minus x plus P of xn minus x. Xn minus x. Xn minus x. T of n. That implies norm xn minus x is as it is. Plus this we need to write norm T of xn minus T of x. Because T is linear. T is linear. Because T is linear. That means T of T is linear. That equal to norm of xn. Norm of xn minus x plus norm of T of xn minus y tends to 0 as n tends to infinity. That implies B1 is complete. It implies B1 is complete. B1 is complete. B1 is complete. Since norm of Tx less than or equal to norm x less than or equal to norm x plus less than or equal to T of x that equal to norm of x1 follows that P is continuous mapping. It follows that P is CTS continuous mapping. Continuous mapping B1 into B dash. B1 into B dash. So this completes the proof. Till here it is enough. So hence proved. Hence proved. Next. Unit 10. Principle of uniform boundedness. Principle of uniform boundedness. Next. Unit 9. Unit 9. Principle of uniform bounded. Uniform boundedness. BDD means boundedness. Uniform principle of uniform boundedness. 9.3.13. One theorem is it? Uniform boundedness theorem. 9.3.1. 9.3.1. Let B be a Banach space. Let B be a Banach space. PS means Banach space. Let N be a normal basic space. N be a normal linear space. Normal linear space. A be a subset of let capital A be a BS subspace of Banach space B, comma n. Set of all bounded linear transformations. The set of all BDD means bounded, LT means linear transformations, B2n with the property T of x such that T belongs to A is bounded subset of n for x belongs to B. Then A is a bounded subset of a bounded BDD bounded subset of is a bounded subset of B. Proof. Here for n equal to 1 into n, 1 to n. Let En equal to x belongs to B, such that norm of T of x less than or equal to n. Clearly, for each n, set En is a closed subset. The set En is a closed subset of B. Is a closed subset of B. Closed subset. By our hypothesis, we have by data. We have B equal to union of n equal to 1 to infinity. En is a set. B is complete by Bayes' theorem. B is complete by Bayes' theorem. By Bayes' theorem. Because there exists at least one set En which is non-empty interior. There exists at least one set En. Which has non-empty interior. interior. The set En contains a closed sphere. The set En contains a the set En means contains a closed sphere S naught. Closed sphere S naught. Closed sphere S naught. With center X naught and radius R naught. With center X naught and radius R naught. Radius R naught. Radius R naught. R radius is R naught. By definition of set En, it follows that by definition by definition the set En, the set En, it follows that norm of T S naught less than or equal to N naught, less than or equal to, for all T belongs to Z. For all T belongs to Z. Here X naught, since X naught belongs to S naught, it follows that S naught minus X naught, S naught minus X naught, which closed figure with the origin is closed sphere with origin, closed sphere with origin. As center and radius are not. As center and radius is R naught. Further, norm of T S naught minus X naught less than or equal to 2 N naught for all T belongs to here. This follows is closed unit sphere. It follows that S naught minus X naught whole divided by R naught is the closed sphere of S. Is closed sphere S, and norm of P S naught minus X naught whole divided by R naught is less than or equal to 2 N naught divided by R naught. 2n0 divided by r0 for all t belongs to A. T belongs to A. That means norm of T of S, norm of T of S less than or equal to 2n0 divided by r0 for r T belongs to A. So this shows that norm T shows that norm T equal to supremum of x belongs to S. X belongs to S. Norm of T of X. Norm of T of X. That equal to norm of T of S. Norm of T of S is less than or equal to 2n0 by r0 2n0 by r0 for all T belongs to A. T belongs to A. The set A is bounded. Hence, A is bounded subset of thus. The set A is bounded. BDD means bounded. Bounded. Hence, A is bounded subset of. Hence, A is BDD means bounded subset of bounded subset of bounded subset of B of B comma N. This completes the proof. Hence proof. So today we will consider three theorems, 8th unit and 9th unit. Those are most important. And 9.3.2. Do it as homework. 9.3.2. Theorem. Do it as homework. Statement book converse of 9.2. Statement. Next, 9.6.2. 9.6.2. Theorem also do it as homework. We discussed in the 2 units, one definition, and 3 theorems. These 2 theorems are homework. Most important, only exam point of view we are discussing here. Thank you very much. Thanks.